So hello, my name is Rainer Hanekamp and the topic of my talk is the JavaScript engine. So the JavaScript engine is the part that executes our JavaScript code. So usually these kind of talks tend to become very technical, but this will not be the case today because I'm a software developer that is using JavaScript to write applications, and I think this is true for the most of us. And therefore, instead of talking about some internals, I think the more important question is what do we as users of JavaScript need to know about the engine so that it executes our code in the right way. And I want to start with a little code example. So as you can see, these are the developer tools from the Chromium browser, and I have 4 objects that represent famous characters from the Star Wars movie with the first and the last name. And I'm putting these 4 objects into an array containing 8 elements, and I also have a function that just returns me the last name of each object. And I call this function 1 billion times, and I'm measuring the execution time with the console object. So if I execute this code, it tells me that the execution time was not 1.9 seconds. So far so good. If we now imagine that these objects come from a database, from a schemaless database, for example, then it might be quite possible that somebody adds a third property, for example, at the Han object. Somebody could add a spaceship called Falcon. And if we execute the code again, then for some reasons we are up to 2.7 seconds, which is about 50% more. The question is now, of course, why is this the case? If we don't know a lot about how the engine works, we might think that this is due to, we had in the beginning an object with only true properties. Now we have added a third one. It might perhaps something have to do with the size of the properties in this object. If this is true, then we can actually very simply verify it. We only need to add this third property to each of the objects. So I'm doing this now. And when I execute the code again, then I'm again down to 1.8 seconds. So for some reason, the code executed faster this time. Depending on your user, you as developer could now say, okay, 2.7 seconds is quite acceptable, and I still continue to work on some other tasks. So if the application runs fine, also it can quite be possible that additional properties are added. So for example, somebody could add to the layer object a property gender. You can say it's female. Sorry, this is look. We say to look, it's a job property with Jedi. At layer we have the gender property. And with Obi-Wan, I could say he's retired true. So if I execute this code again, we are up to 3.3 seconds. So again, the question, is this still acceptable to our users? If yes, we don't care. But for some reason, it can happen that one day we are called, there is an urgent event, for some reasons the application does not work. And if we look at the code, we see that somebody has added a 5th object. I call it Yoda. And since I don't know the first name of Yoda, I just say it's an object with the last name. And I also have to add Yoda to the array. So I execute again. Yeah. The machine gets louder a little bit. So, and we're up to 10 seconds. So this is now something that we cannot ignore anymore and we have to fix. So I will come back later to the reasons why this happens or what the strange thing is about it, but first I want to say a little bit about JavaScript as language itself. So in comparison to other languages, for example, like Java, JavaScript has the reputation to be badly designed. There is a reason why there exists a book with this name, the good parts. This means that there are always some bad parts. And also in terms of execution speed, JavaScript is not the fastest. So this might not be true with the latest browsers, but still, as we have seen, there are quite some edge cases. So the question is, why is JavaScript as it is? And surprisingly, the reasons for this are not technical ones, but political ones. And we would have to go back to the very early first days of JavaScript, and actually to the year 1996. So 1996 is the year where Microsoft was at its peak. They had just released Windows 95. And there was a small company called Netscape that sold server-based software, but also provided a browser for end users. And of course, Netscape had this business interest that they wanted to bring more and more users to use their browser, because that also means that the demand for the server-based software increased. And how can you do this? Well, you just require some applications, and if you want an application, then you require perhaps a programming language. So Netscape decided that they wanted to create a programming language. At the same time, there was another company that has just released a brand new programming language a year before, and this programming language was extremely hyped. It was seen as the successor to C++, which was these days the standard language. And it also had a quite catchy slogan, namely write once, run everywhere, which means that you as developer only had to write your source code once, and your application could be run on different operating systems, but more interestingly also on the browser. So when Sun, I've already said it, so the company was Sun, and the programming language was of course Java. So when Sun heard that Netscape is going to release or to create their own programming language, they called them and said them, look, if you want to create your own programming language, then we will not allow you to use Java. And so Netscape said, okay, and tried to negotiate some compromise. And the compromise was that Netscape said they will design a language which only targets small applications, so only something like animations, or blinky stuff, or form validations, but nothing more. And their programming language targets only, should be very easy to use. This means that you don't have a compiler, you also don't have static types, and it is very easy to run. And of course, if somebody wants to create a real application, then they should of course use Java. And then there was Sun that really was behind this decision, because Netscape now implicitly said we will call our language Java and script, so JavaScript. And as we all know, a script is usually just a few lines of source code, and the name already dictates that it isn't targeting larger applications. And JavaScript was released in 1996 with the Netscape Navigator. So this was the situation for quite many years, until in 2004 the unthinkable happened, because somebody released a real major application for the first time to the major public, and they only used JavaScript. And the company that was behind this was Google, and the application was Gmail. So for the first time we knew that it was possible to also use JavaScript for real large applications. The main problem was still the execution speed, because at this time the main browsers, Internet Explorer and Firefox, were simply too slow. So everybody that was planning to write applications in JavaScript knew it would not run very fast. This lasted until 2008, and again it was Google that released an own browser because they saw that the other browsers weren't doing that much, and they called it Chrome. And I would say this is actually the beginning of the era of modern browsers, because from this day on also larger application or JavaScript in general was executed really fast. So the question is, what did Chrome have what others were missing? It was a superior engine, because you cannot change JavaScript as language, because there is something called backwards compatibility. So you don't want that all users of JavaScript have to rewrite your applications. So if you really want to speed up the execution, then you have to work on the engine. So what is the engine? As I have already said in the beginning, it executes JavaScript source code. It is usually bundled within a browser, but it can also run separately. It should not be mistaken with the rendering engine, so this is something completely different. And usually each major browser has their own engine these days. So with Chrome we have V8, with Firefox we have SpiderMonkey. Microsoft names its engine Chakra Core, and Apple has JavaScript Core. And as most of us probably know, V8 can run separately, and this is also the engine that is behind Node.js by default. So the question is again, what's the secret of an engine? What did Google do that they really increased the execution speed? Well, what they did was that they used both an interpreter and a compiler. So the interpreter, as we know, loads your source code, it parses it and executes it more or less on the fly. So there is a real quick startup of the application. With the compiler on the other side, you have a very long, relatively long compilation phase, but during that compilation phase, the compiler can actually analyze your code, it can find some patterns for optimizations, and after that the compiler generates machine code, and machine code, when executed, is by far faster than interpreted code. As we all know, JavaScript is deployed with source code only. We do not have a compiler, so how can this work? This is not just a small screen, so on the left side we have the source code, and on the right side you see the interpreter and the compiler, which is placed within the engine. So the first step is, of course, that the source code is loaded into the interpreter, and the interpreter, as I said before, immediately starts with the execution. So the application runs. As the interpreter executes the program, it knows which parts are executed very often, and it marks these parts as hot code. And this hot code is then passed on to the compiler, as we can see here. And the compiler now analyzes this code, optimizes it, and generates machine code. And as soon as that machine code is ready, the engine uses that machine code for execution and does not fall back to the interpreter, but only for the optimized part. So far, so clear. As you see, there are quite some optimizations going on, and there is one major optimization technique that we should all be aware of, also for just application developers. Sorry for the just. And that's called inline caching. And if I would have to describe inline caching in one sentence, I would say it is integrating static types during the runtime. And as you can imagine, this is quite a challenging task, not very safe, and therefore I think that this image is quite fitting. Okay, so how can this work? So this is the status that it was before Chrome was released. JavaScript was only interpreted, and as you can see, we have here again our four objects from the beginning, and the function on the right side. So the problem is now that our function needs to return the value of this last name property. And as JavaScript is dynamically typed, the interpreter has no chance to know what objects are passed. So you can virtually pass everything what you want. So the interpreter has to search for this property at each call, which means in JavaScript, the property can be somewhere deep in the prototype chain. You can have getter methods or proxy. So basically this means that this execution, this lookup execution for the property is a real expensive task. It takes a lot of time. Now with Chrome, something new was added, and this is called hidden classes. And hidden classes are not a concept of JavaScript. This is just when JavaScript executes, and it is an element inside of the engine. Now each object is assigned to a hidden class, as you can see here, and the criteria if two objects share the same hidden class is they have to have the same properties, in that case first name, last name, but the properties also have to be in the same order. So if the first would be last name and the second one would be last name, this would be a different hidden class. The term hidden class these days is also replaced by object shade. The reason is quite obvious, because for some years we have classes in JavaScript and people tend to mistake the hidden class concept with the JavaScript class concept, and therefore nowadays you often find also the term object shade, which is the same. So all these four objects are assigned to the hidden class P1. And additionally, there is this guy on the left side, and that is the profiler. And the profiler is watching the execution and is recording the hidden classes that are passed to this function. And as you can see in our case, it is always P1. And this code, so currently it is still interpreted, but now the code is passed on to the compiler. The compiler generates machine code, and what the optimization now is that the compiler says, okay, I know that all the time I'm getting a P1. I know how P1 is constructed, so I can already know where the memory location of this last name is. And I know that all the time the last name property is required in my case. And therefore, instead of looking up or searching for this property, I just return the value that is on this particular memory address. And this is extremely fast. So there is a small catch, because if our, as we have seen also in the example, if an object gets an additional property, like in this case with Han, where we have the spaceship, then Han is assigned to a different hidden class. In that case, it is called P2, which means that our profiler now sees a P1 and a P2 hidden class. So far, this is not a real problem, because the generated machine code now has to check. So the machine code now just checks if the passed object is of type P1, then return the memory address where we know where it is according to P1. If it is P2, to the same. This works up until 4 hidden classes. The problem is when you exceed these 4 hidden classes, then things change. And this was what caused the 10 seconds in our example in the beginning. As you can see, we have now 4 objects with this Yoda type, a Yoda object, and all the other objects have different properties. So we have now 5 different hidden classes. Still the profiler is still recording what's going on, but in difference to the former example, the generated machine code does not store the memory location anymore locally inside the function or inside the call side. And it has to look up the memory address of our property in a so-called global cache. And this takes quite more time than it would be if the machine code would have direct access to the memory location. And that's why we saw the decrease in performance. So summarized, there are 3 different types of inline caches. The first one is monomorphic. This is the fastest one. It works best, or it is monomorphic. You have the monomorphic state if only one hidden class is passed. Polymorphic goes from 2 to 4. It is a little bit slower, but still acceptable. But the real problem is if you are in a megamorphic inline cache, because then we have to look up the property or the hidden class in our global cache, and this decreases our performance tremendously. So as we now know what caused this strange behavior in the beginning, we can also try to solve it somehow. So as I have said, the key here is that each object has the same properties and they also have to be in the same order. And the way we can solve this problem here is that we, for example, create an own class. And so I just write class person. And this class has, of course, a constructor. And what we have to do now is that we have to pass all possible properties for this person in this constructor. Which means I'm writing a first name, last name, spaceship, job, gender, and retired. And what is also important is that I'm not just assigning the value, but I also have to set a default value which has already the correct type. Because it is not said that every time the value is passed to the constructor. So it looks like this. I have to say first name or empty string. This last name, or empty string, and so on. I have already prepared the solution. So it looks like this. As you can see here, please mind that the retired is a Boolean, so you have to assign a Boolean value, and you call or reinstantiate this class with the usual new command. And as you can see here, I can pass null values. This is perfectly fine because if it is null, we are assigning a default value. So as we have seen before, we had 10 seconds, and if we execute this version, we are at 1.8 seconds. So this is actually the same execution speed that we had in the beginning with monomorphic cache. Okay, so summary, we are already at the end. As I have said, engines combine an interpreter and a compiler. The interpreter gives us the fast application startup, and the compiler gives us the fast execution of the generated machine code. Inline cache is one of the main optimization techniques, and it works best if you're using static types, so if you don't change the types all the time. There are also other optimization techniques that I didn't mention, but be assured they also work if you are using static types. And the solution might be that you're using JavaScript classes or just switch to a language that has types included, for example, TypeScript.